Hello, everybody. Welcome back. This is Solving Stuff with Sosa, episode 8. And what are we going to be doing in episode 8? We're going to be talking about Thevenin and Norton, specifically their theorems. And we're going to be doing some circuit analysis using Thevenin and Norton theorems. But I'm kind of tired today, so I've invited a couple of very special guests to help me explain Thevenin and Norton by way of solving a couple of problems relating to circuit analysis. So, without further ado, let them introduce themselves.
I'm Scorpion, and get over here. I'm going to be talking about Thevenin. I am Sub-Zero, and I will be speaking about Norton. For this circuit, we will find the Thevenin equivalent voltage across terminals A and B. For this, we will first establish the meshes in the circuit. Mesh 1 will have a current I1 going through it, which will be established as going clockwise. Mesh 2 will have a current I2 going through it, which we will also establish as going clockwise. We will analyze these two meshes using Kirchhoff's voltage law. For mesh 1, we have the 2-volt power supply where the current is going into the positive. And so we have 2 volts. We also have the 2 ohm resistor to the left where current I1 is flowing. And so we have 2I1. Lastly, we have the resistor of 2 ohms in the middle where 2 currents are flowing, I1 and I2, and these are going in opposing directions. And so we have 2I1 minus 2I2, and according to Kirchhoff's voltage law, these have to be equal to 0. We may simplify this expression for further use. And now in mesh 2. In mesh 2, we have a 2 amp power supply where we have a voltage AB that goes across it. This voltage AB is actually the one we're looking for. And so we have VAB. We also have the 2 ohm resistor in the middle where we have 2 currents going through, as we mentioned before, but now we're doing the analysis in mesh 2, and so it will be 2I2 minus 2I1, and this is equal to 0. Since we're looking for VAB, we will solve this expression and simplify for VAB. And now we notice that for the 2 amp power supply, we have a current I2 that is exactly the same as the 2 amp power supply. And so we can identify one of the values, which is I2, and this will be equal to 2 amps. We take this value to the simplified expression that we found in mesh 1, and we may find the value of I1, which is going to be 0.5 amps. We take these two values and substitute them now into the expression for VAB that we had found previously, and we find that the voltage VAB is minus 3 volts. And so the Thevenin voltage is the one that's going across terminals A, B, and so the Thevenin voltage is minus 3 volts. And so this is equal to this, which is what we were looking for. Answer A. Get over here. But this is not over yet. I actually didn't know I was going to be invited to do these videos in Mexicali. It's really hot. So, since we're here, let's do an extra problem that has to do with Thevenin. And so for this extra problem, we already calculated the Thevenin voltage across terminals A and B. Let's now calculate the Thevenin resistance across terminals A and B. The first step to calculating the Thevenin resistance is to eliminate the power supplies. And so we eliminate the power supplies by putting the voltage sources as a short circuit and the current sources as an open circuit. This now generates a new array where the two 2 ohm resistors are connected in parallel. And so we calculate the parallel resistance between terminals A and B, and that is going to be equal to 1 ohm. We also can remember that the parallel equivalent resistance of two resistors connected in parallel with the same value is going to be half of that value. And so the Thevenin equivalent resistance is going to be 1 ohm. Get over here! What we will do now is find the Norton equivalent current and resistance for the circuit that is shown. The first thing we will do is calculate the Norton current that is going between points A and B. We will do this by closing the circuit between those 2 points and finding the corresponding current. As we see here, once we close the points A and B, a virtual short circuit is generated and the 5 ohm resistor ceases to have any effect in the circuit. Therefore, we are left with an equivalent circuit where the 5 ohm resistor can be eliminated. And so we now have a current between points A and B that we may calculate. We can do this using node analysis, either node A or node B, if we analyze the currents that are going in and out of these nodes, and we will do this by using Kirchhoff's current law. We notice that 2 amps are going in. These correspond to this current source. 2 amps are going out that correspond to this current source. And IN, which is the Norton current, is the one that is going out of the node. Therefore, we establish this equation: 2 amps going in, 2 amps and the Norton current going out. The 2 amps cancel each other out, and we are left with a Norton current of 0 amps. And so now we will calculate the Norton equivalent resistance by eliminating the voltage and current sources. We eliminate the current sources by putting them in an open circuit. This way we eliminate both of them. And we notice that when we do this, the 5 ohm resistor that's to the right is left connectionless. This means that the 5 ohm resistor now has no effect on the circuit, and thus we are left with just one resistor, this 5 ohm resistor that's connected to terminals A and B. And therefore, the resistance between terminals A and B is 5 ohms. This resistance is the Norton equivalent resistance. And so this is equal to this. We had already found that the Norton current was 0 amps, and so this is equivalent to this, and therefore the answer is E.
Well, that was certainly odd, or at least different. Well, I'd like to give a special thank you to our 2 special guests, Mr. Scorpion and Mr. Sub-Zero. I'm particularly grateful because they came all the way over here to Mexicali to do this recording, and it's pretty hot down here, and they're wearing hoodies, and so thank you to both of them for taking time off from their very important schedules and responsibilities to talk to us a little bit about the Thevenin and Norton theorems via a couple of examples there. Thank you so much. Well, this has been Solving Stuff with Sosa, episode 8. I hope you enjoyed it. I hope you learned something. Let's make this viral. See ya.